السلام عليكم، مرحبا بالجميع. نتابع في سلسلة محاضرات تحليل حقيقي واحد. محاضرة اليوم عن المتريك سبيسز. المتريك سبيسز عبارة عن ست أو نون امتي ست معرف عليها اقتران real valued function الكارتيزيان برودكت تبع الست المراد التعريف عليها، ويحقق 3 شروط. خلينا نبدأ بالديفينيشن للمتريك سبيس ونشوف أهمية المتريك سبيس في الريال أناليسيز in general. Chapter 2 Metric Spaces. Let us start with a non-empty set X and define a distance function. Usually we call this function a distance function, and define a function or a distance function d from X Cartesian product with itself into R plus, where R plus denoted to the set. Zero, infinity. We call XD metric space if the following conditions hold. The first property is that the distance between any 2 points X and Y is always greater than 0, and the distance between any point X and itself is equal to 0. This is hold, or this is true for all X and Y in the space or in the non-empty set X. The second condition the distance between any 2 points X and Y is the same as the distance between Y and X. This is called the symmetric property for all X and Y in X. The third and the hardest property is the triangle inequality. The distance between any 2 points x and y is less than or equal the distance between x and z plus the distance between z and y, and this is true for all x and y and z in x. So that if all these conditions hold, then we call the metric space XD metric space. We call it metric space. If one asks why I need to define such space, what is the benefits? ايش الفائدة من تعريف المترك سبيس؟ لو ايش مهم؟ simply ببساطة in any space we create or we need to deal with, we need to know the geometric or the structure properties in this space. The algebraic properties, as you know, can be studied in the sense of abstract algebra in separate course. However, here we study the analytic properties and also as well as the geometric properties. In any space X, the elements of any space, as you know, is points. Any space has a point. The main function or the main importance of the metric space or the function D is to study the distances between the points in this space, and the distances between the sets or subsets in X. What is the shape between any 2 points or between any 2 subsets or between any point in X and another set E subset in X, but it's not include X. All these properties we have to study. Simply or roughly speaking, the metric space give the geometric properties of the elements of the space. To study this space, firstly we need to do some examples about famous metric spaces, and then step by step we are going to do some definitions related to the points and the sets in this space that regulate the relations between these elements in the space. The first example we have here is the following. The first example. Sample 1. Let x, let us write in black, let x be non-empty and define D from x cross x into R plus, given by the distance between any 2 points is 1 when x not equal to y and 0 when x equal y. Let us check whether this metric is metric space or not. Solution. So that we need to check the 3 conditions here. We need to check the 3 conditions here. The first condition, clearly, by definition of D, the outcomes of D is always positive, or we can say non-negative, greater than 0 and equal 0 if the distance, if we measure the distance between the point to itself, between 2 points, 2 similar points. First condition. Let us first try let x and y in x. If x not equal to y, then by definition of D, the distance between x and y are equal 1, which is greater than 0. So that the first condition, the first half of the first condition holds. Moreover, the distance between x and it itself is equal to, as you see, 0. So we already have the first condition. The second condition, which asserts that the metric must be symmetric. Let us check the distance between x and y equal to 1 when x not equal to y and x equal to y is 0. And this is the same as 1 when y not equal to x and y equal to x 0, which is exactly the distance between y and x. So that this is whole, i.e. D is symmetric. D is symmetric. You can write here the name of each property. This is positivity. If you need to know what's the name of this property, the first one is positivity. The second one is symmetric. The third one satisfies the triangle equality. Triangle inequality. Okay. It remains to prove or to verify the third condition. Simply let x and y and z, let x and y and z in x. As you see, we need to check more than one case because we have the definition of D in terms of 2 points in x. So we need to check when x, the elements x and y and z are different, totally different, or the second one, sorry, are all equal. The third case is to check when 2 points pairwise are equal but not to the third, but not equal to the third. Case 1. Assume x, this is the trivial case, x equal to y equal to z in x. Clearly, the distance between x and y is equal to the distance between x and z, which is the same as the distance between z and y, and this is equal to 0 by definition of D. By definition of D, x equal y 0, x equal z 0, x y equal z 0 by definition of D. By definition of D. Case 2. Assume x not equal to y not equal to z in x. So that the distance between x and y, which is 1, this is less than or equal the distance between x and z, which is 1, right? Plus the distance between z and y, which is also 1. Here we have plus 1 plus 1 is 2, which is greater than 1. And the second case holds true. The second case, or the third case, sorry, case number 3. Let us take arbitrary points x and y and z such that let x, y, z in x be arbitrary points. Be an arbitrary points. Be arbitrary points without loss of generality assume that we have two equal points, say x and y, x equal to y, but not to z. Therefore, the distance between x and y clearly 0, which is less than or equal the distance between x and z, which is 1, plus the distance between z and y, which is also equal 1. And this is 2, which is of course greater than 0. What if one chooses x equal to z, not to y? Similarly, if one chooses x equal to z, not to y, let us see what happens. The distance between x and y is equal to 1 because we have x not equal to y. Is it true that this distance less than or equal the distance between, sorry, this is equal to 1 this is equal to 1 which is less than, we need to verify that, the distance between x and z plus the distance between z and y. Clearly, the distance between x and z is 0, and between z and y is 1. 0 plus 1 is equal to 1. So that we have equality. We have equality. The same case hold if one replace x by y, i.e. if one write similarly if we have y equal to z not to x, we will get equality between the distances, and this finish the proof. There is no more than 3 cases in this third condition, triangle inequality. In the triangle inequality, let us check another example. Sorry. Assume let x equal r, the real numbers, and define the distance between x and y is the absolute value between these 2 points. We need to show that this is metric, or let us say we need to verify that this metric or this set form a metric space together with D. Show that X and D form a metric space. Let us go directly to the solution. Clearly, we need to check the 3 conditions. Let X and Y in X, which is R, the whole real numbers, with X not equal to Y. Clearly, the distance between X and Y is equal to the absolute value between X and Y, X minus Y in the absolute value, which is of course greater than 0 because the absolute value. The second one is to check the distance between the point and itself, which is holds 0 clear. So the first condition is satisfied. Here, the first condition. The second condition, let X and Y in R be any points. be any points. The distance between x and y clearly is equal to the x minus y absolute value of x minus y and this is equal to the absolute value of minus x, y minus x, and this is the distance between y and x, which is symmetric, symmetric. The third condition, before we prove the third condition, we need to recall that for any x and y in R, the triangle inequality for any p, let us change the notation. For any a and b in R, the absolute value of a plus b is less than or equal the absolute value of a plus the absolute value of b. We will use this inequality. This is celebrated inequality called the triangle inequality for reals. Now, let x and y and z in R, we need to check the distance between x and y is less than or equal the distance between x and z plus the distance between z and y. And this is true because by definition of the metric function, this is equal to the absolute value of the difference between x and y. Let us add and subtract the element z inside the absolute value, which gives x minus z plus z. Just I inserted negative z minus z and plus z inside the absolute value here, plus or minus y. Let us call this A and B, right? This is A and this is B. By the triangle inequality, the absolute value of A plus B is less than or equal the absolute value of A plus the absolute value of B. And this gives the absolute value of x minus z plus the absolute value of z minus y, and this is exactly the distance between x and z plus the distance between z and y. So that we have the triangle inequality. The distance between x and y is less than or equal the distance between x and z plus the distance between z and y. By 1 and 2, by 1, 2, and 3, we have verified that the given metric is real metric space. Thus, 5, 1, and 3, x, which is R, and D for a metric space, which is usually called the real metric space or the usual metric space. Usual metric space or the real metric. Let us go back to the first example here. This famous example, D, is called the discrete metric. The discrete metric space over any non-empty set X. Okay? Let us go to another example. Let us determine whether the given metric the given distance function, the given function for a metric space together with R. The metric is given by let X, R, and D X and Y is equal to the square difference between these elements. Let us check. Clearly, the first condition holds because we have the square. Because we have square on the difference. Clearly, for any X and Y in R, the distance between x and y, which is x minus y squared, is greater than 0, and the distance between x and itself is equal to 0, so that the first condition holds. Thus, the first condition holds. The first condition holds correctly. The second one, this is the first, the second. Similarly, we have for any x and y in R, the distance between x and y is equal to the square difference between the elements x and y, which is the same as the difference between y and x squared, and this is the dyx. So D is symmetric. Okay. How about the third condition? We need to verify, that the third condition holds for any x and y and z in R. However, if one chooses x equal to the 1 and y phi and z equal to 2, then we have the distance between x and y, which is the square difference between x and y, and this one minus 5 squared, which is 16. The difference between x and z is x minus z squared. Which is 1 minus 2 squared, and this is 1. The third one, the difference between the x and between z and y to the power 2, which is equal to 2 minus 5 squared, which is 9. So, is it true that the distance between x and y is less than or equal the distance between x and z plus the distance between z and y? As we have seen here, the distance between x and y is 16, which is not greater than the distance between x and y, which is 1, plus the distance between y and z, which is 9. The sum of these distances is 10, which is not greater than 16. So D is not metric. So that hence from 3, the triangle inequality pair so that x or r with the given D is not metric at all. This is the paired example. To point out this paired, this is the third, and the previous one is the second. It remains to define metric on higher dimension of R or any set rather than R. Example 4. Let X R2 and D is the metric defined as the distance bonds, the distance between the bonds in the plane, which is given by the square root of x1 minus y1 plus x2 minus y2 squared where x is vector, two-dimensional vector given by x1, x2, and y is the vector y1, y2. Show that x, which is r squared, together with the four emitter. The first two conditions clearly hold, right? The first one, this always greater than 0 and equal 0 if x equal to the vector y. So we done in the first condition. The second condition is also hold trivially. Replace x1 by y1 and x2 by y2, then we get the symmetric property for D. The hardest condition is the third condition, which is about the triangle inequality for the this metric space. So I will leave this to first condition solution. Try yourself with the first two conditions. The important thing is to verify the third condition. Let x equal to x1, x2, and y is the two-dimensional vector y1, y2, and z equal to z1, z2. Of course, in R2. Sorry. We need to show that, sorry, the distance between x and y is less than or equal the distance between x and z plus the distance between z and y. The underlying element here is denoted to the vector x1, x2, or y1, y2, or z1, z2. Indeed, we can prove such inequality, but we need to recall some facts about famous inequalities in between real numbers. It happens in such cases in metric space or other similar spaces. We need to use some celebrated inequalities such as Holder inequality or Minkowski inequality or the AM-GM inequality. For this kind of inequality, we need to remember the Minkowski inequality. Let us recall what is the Minkowski inequality. Simply, if we have any two complex numbers or real numbers, recall that let us call this star. Recall that for any finite and indeed infinite, for any finite two positive for any two finite for any two finite for any two finite for any two finite sequence of positive real numbers, we have for any two finite sequences of positive real numbers, let us say here AK and BK. AK, BK, we have the summation between the terms of the finite sequence AK and BK to the power P from 1 to n one P is less than or equal to the summation between the first term sequence AK, P to the power 1 over P plus PK to the power P to the power 1 over P from 1 up to n. For all P greater than or equal to 1. This is all for any P greater than or equal to 1. In our case, we need N to be 2. In our case, let us write. The distance, now, the distance between x and y as vector equal to the square root of x 1 minus y1 square plus x2 minus y2 square. As we have done before this trick, I will insert z1 minus positive. I will add and subtract z1. Similarly, I will add and subtract z2. So this become the square root of x1 minus z1 plus z1 minus y1 square plus x2 minus z2 plus z2 minus y2 square. Now, let us set x1 minus z1, a1, and x2 minus z2, a2, while z1 minus y1, p1, and z2 minus y2, p2. So by the above inequality here, the index is from 1 to n, which is 2 in our case. A1 plus P1 to the power P, which is 2 in our case also. This is 2 in our case, right? Plus A2 plus B2 to the power 2. All these summation to the power 1 over 2, or the square root. This is less than or equal A1 plus A2, right? A1 plus A2, right? Square each of which square? A1 square, A2 square, 2 to the power 1/2 plus the square root of P1 square, P2 square, right? And indeed, this is equal to x1 minus z1 square plus x2 minus z2 square, which is the distance between x and z, plus similarly here the distance between z1 minus y1 square plus y2 or z2 minus y2 square, and this is the distance between and this is the distance between z and y. Which proves our inequality, the distance between x and y is less than or equal the distance between x and z and y. This is the example. Hence, r squared r squared together with the form a metric. This is an example for two-dimensional space with the real metric. This is called the second dimensional space in calculus. We can extend this to n-dimensional space by considering extending the form of the given metric space. For that, we can write as example homework. Let x Rn, and n is integer greater than 1. Define let and d is the distance between the vectors x and y, which is given by the formula summation between 1 to n for xi minus yi square to the power 1 half. This is the Euclidean metric space in n-dimensional space. Okay, we will stop for now and we will continue in the next lecture. Hope I can help you in this topic. And I am glad to help you to understand the concept of metric spaces. Next lecture we will talk about the neighborhoods. Thank you for your attention and bye for now.